part 3 of the periodic table. So we talked about trends. Atomic radius going down and across, electronegativity going down and across, ionization energy going down and across. So what we're going to do right now is talk about the groups going down. Remember, groups were also called families because they all have similar chemical and physical properties because of the number of valence electrons. So group 1 is called this. Group 1 is called the alkali metals. All right? And so, group 1 is the alkali metals. They have one valence electron. Their electron dot looks like this. Any element in group 1 has one dot, which means S1. So the electron configuration for the valence shell in group 1 is one dot, which is S1. Okay? Number 4. They are never, ever, ever found in nature by themselves because they're way too reactive. So the reason they're reactive is the easier it is to lose an electron, the more reactive it gets. And this is the biggest group of metals in the whole periodic table, which is number 5. This is the largest group, size-wise, of metals, the most reactive group of metals. It contains the biggest metal of all. Francium is the largest metal and it's the most reactive simply because its valence shell is way out there, number 7. It doesn't want, it's an electron, doesn't take very much to rip it off. So it is super reactive, super explosive. And the weird part about group 1 metals, they float. But the big deal is, you put them in water, they do float, but they explode. So, extremely strong, very reactive metals. They all want to lose one electron. That is group 1. Now, group 2, right here. These are called the alkaline earth metals. These are the second, this group is the second largest size-wise and the second, which is the most reactive. Second largest and most reactive metal group. 3, like group 1, never found in nature alone. So groups 1 and 2 are never ever found in nature alone. Well then, how do we get individual elements like sodium and magnesium and calcium? Well, there's a process called electrolysis. So if you chemically put together a compound, you can chemically break it apart. And electrolysis breaks apart like NaCl, so you get Na substance and Cl substance. Okay, so that's about it, except for number 4. What the electron dot looks like would be X with 2 dots, and that equals an S2 configuration. S2 configuration, remember group 1 was an S1, 1 dot, group 2 is an S2, 2 dots, all right? So that's the alkali metals, alkaline earth elements. All right, next. The next is right here. Groups 3 through 11. Groups 3 through 11, there's a lot of stuff about this. These are called the transition metals. All right, so we got a bunch, groups 3 through 11. We're going to go over this right now. These have some very weird properties. First of all, the most important property is they have 2 overlapping valence shells. That's because most of them have an unfilled D subshell. So they can lose electrons from the unfilled D, and they can also lose electrons from their valence shell. So this overlapping valence shell gives rise to this. It gives rise to multiple oxidation states. That just means multiple charges, okay? Like this one, like manganese, Mn. Mn, it can do this. Lose 2, lose 3, lose 4, or lose 7 to become stable. So these are multiple oxidation states due to overlapping valence shells, okay? And one more crazy thing about the transition metals. This is number 5. Their ions form colored solutions in water. So copper is a bluish color, gold is like a yellowish color. So all these transition metals, if you see a colored solution, there's a transition metal in there. Okay, that's about everything you need to know about the transition metals. Okay, now group 12 is not considered transition because it has a filled D subshell, but you don't have to worry about that. The next group would be right here. These elements, B, Si, Ge, As, Sb, and Te, are considered metalloids or semi-metals. Now, think about this. From these over, they're all metals. 2/3 of the periodic table are all metals. From here over, they're non-metals. Well, you can't just go from a metal right to a non-metal. It's like a demilitarized zone. So you have the metals, then you have the transition metals, you have the metalloids, which have properties of both metal and non-metal. All right, so we have the metals, we have properties of both metal and non-metal called the metalloids, and then we have the non-metals. All right, so that takes care of that. Now, we'll keep on going. Group 13, all we need to know is this. Group 13, they all look like this. They have a pair and a single, and that is from an S2P1. Remember, we're only talking about the valence electrons. S2P1, so they have 2 in the S and 1 in the P. That's what it looks like, group 13. Okay, now we go to group 14. So there's group 13. Now we go to group 14. And there's one very strange element, and it's right here, which is carbon. Group 14, let's do it. They should look like this. They should have a pair, a single, and a single, which means their valence electrons in their outside shell, they should have 4 valence electrons, and they should look like this, an S2P2. Don't forget, the S2, 2 electrons in that orbital. P has 3 orbitals, but there's only 2 there, so it looks like this. So there's your pair, and here are your 2 singles. That's what all of the elements in group 14 should look like, but they don't. There's only one weird one, and that's carbon. So watch what carbon looks like. This is number 2. Carbon should look like that, but one of these electrons in carbon from the S, one of the electrons in S, moves right here into the P. So it moves down. So now carbon looks like this. 1 S and 3 P's. So this configuration is S1P3. And that's the only one you have to worry about in Regents Chemistry in New York. It's called an sp3 hybrid bond orbital. Don't worry about that. Just know that carbon, each corner, 12, 3, 6, and 9, has an electron. And that is group 14. Now, group 15. Group 15 is very interesting. Group 15. Because group 15 starts out as a non-metal, and then we go non-metal, non-metal, then we go to arsenic, which is a metalloid or transition metal, and then here's the biggie. Bismuth. So we're going from non-metal, non-metal, metalloid, metalloid, finally to a metal. So this group is always S4. Make sure you know group 15 starts non-metal, and as the size gets bigger, you know the bigger the atom, the more metallic it gets. So that's what's happening with that one. So we'll write that down, group 15. And that's what's happening right there. So group 15 starts out with 2 nonmetals, they go to 2 metalloids, and finally, the biggie is at the bottom of the group, we have a metal because the atom's so big, and it's bismuth, okay? Very interesting group. That's group 15. All right, group 16 right here. Oxygen. Wickedly electronegative. Remember, oxygen has the ability to attract electrons. It's very, very, very good. It's one of the strongest electronegative elements on the periodic table. Okay, so let's look at group 16. Group 16 looks like this. 4 electron dot. It's got a pair at 12, a pair at 3, single, single. And how come? Because the valence shell of group 16 looks like this. The S2 and P4. So we have this. S2 filled. That's this one at 12 o'clock. P4, 1, 2, 3, 4. So the S2 is at 12. This first orbital in P is here, and then we have 2 singles. So all of group 16 looks like pair, pair, single, single. And like I said, oxygen, probably the second most electronegative element on the whole periodic table. It is wickedly strong. Okay, that's group 16. Group 17. Group 17, they are called the halogens. And I'm sure you may have heard halogen headlamps. They have halogen gas in them, and they're pretty bright. Okay? Also, the halogens, I call it the antiseptic group because they help kill bacteria. All right? All right, let's look at these. Halogens, here's what they look like. They have a pair, a pair, a pair, and a single. So the electron configuration in the valence shell, S2P5. So let's check that out. S2, that's at noon. P1, P2, P3, P4, P5. So these 3 are pair, pair, pair. That one right there is that single. So they only need 1 more electron to have a stable octet or look like the noble gases. All right, so that's there. So let's put down number 3. Number 3, this is a very strange gas, a very strange group because they have all 3 phases of matter. F2 and Cl2, gas, Br2 is a liquid, and that's at room temperature, but when the bromine liquid evaporates, it turns into a diatomic gas. Ni2 is a solid. Really weird. And when this solid sublimes, which we'll talk about in a second, it turns into I2 gas. So these are all diatomic gases. All right? So we have two gases, one liquid, one solid. Now, I said the word sublime. Iodine sublimes. That means it goes right from the solid state right to the gas. It skips the liquid state. All right, that's the only element on the whole periodic table that does that. The only other element, the only other substance you need to know that sublimes is this one, CO2. CO2 also goes from solid to a gas. Those are the only two. So this is like the antiseptic group. Remember, fluorine is in your toothpaste and it's in most people's drinking water. It makes your teeth hard. Chlorine, obviously, swimming pools and all that, it kills bacteria. Bromine and iodine, same thing. All right, bromine tablets, you put them in water to kill everything in water if you don't have pure water. Iodine, when I was a kid, there was this stuff called mercurochrome, had iodine in it. Iodine kills. It really burned, but it kills too. All right, so we have group 17. Remember, they only need one electron to become stable. Finally, we have group 18. These are the noble gases. And there's other names for them too. So we're going to go over all these. Group 18. So we have three names. We have the noble gases, we have inert gases, and then we have monatomic gases. All that means is, inert means they don't want to bind with anybody because they are stable. They are very cool. They're noble. Every element on the periodic table wants to look like them. Not proton-wise, not neutron-wise. Every element on the periodic table wants to look like them electron-wise in the valence shell. So the majority of the elements on the periodic table want to have a stable octet, which means 8 in the outside shell. Some want to look like helium's configuration, which they have only, helium only has 2, but that fills the first shell. All right, so every single element on the periodic table wants to have a noble gas configuration. So, what else about the noble gases? We said this for number 2. Almost all of them have a stable octet, so here's what it looks like. We're going to have an X, and then we're going to have pair, 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 pair. So that is an S2P6. So every single one, look. Pair, 1, 2, 3, 4, 5, 6. So all 4 orbitals are filled. That's the stable octet. But remember, we have helium also. So we're going to go 3 He, and He has this, which is this, which is this. So helium is the most stable element on the whole periodic table. Nobody can rip it off because it has a full first shell and it's closest to the nucleus. the most stable element on the whole periodic table. All right? Now, if we look, helium's up here, and then we have neon, argon, krypton, xenon, and radon. Well, you see, let me do this. Remember the reason helium split off from the other noble gases is it only has two, but that fills the first shell. Now look at, it doesn't want to do anything. It doesn't want to do anything. It doesn't want to do anything. This could do something. So, no chemical activity at all, no chemical activity at all, no chemical activity at all. And then krypton, xenon, and radon, these two do have some chemical activity because they're so big. So that means that they could possibly get ripped off. But the first three, helium, neon, argon, can't be ripped off. Okay? Those are the groups on the periodic table. Now, for the periods, if you look, remember period is also considered energy level or shell. So in the first shell or energy level, we only have two elements. And both these elements are gases. We have hydrogen, which is H2, that's a diatomic gas, and we have helium, which is a noble gas. So period one, only two gases. Period energy level or shell 2, we've got the strongest electronegative element on the whole periodic table, which is fluorine. Remember, fluorine only needs one electron. It's small, so it really can steal electrons. All right? Period 3 or shell 3, that's just metals over here. It's got a metalloid, it's silicone, and then we have non-metals on the other side. There is also some weird stuff going on with some of these periods. Like this one. Period 4, well, we have arsenic as a metalloid, but we have bromine as a liquid, and we have krypton as a gas. So period 4 also has all three phases of matter, just like group 17 has all three phases of matter. All right? So, mainly most important are the groups, and we went over some of the periods, so that'll be it for the periodic table right now. The other thing that we do have to talk about, and it's always on tests, is metals always want to lose electrons. All right, metals always want to lose because you can tell by the positive charge that means they lost negatives. Non-metals, most non-metals want to gain. So we will end this video with this. Which is larger for a metal? Its atomic radius or its ionic radius? For a metal, the atomic radius is larger because in order for a metal to become an ion, it's got to lose electrons. So, atomic radius larger than ionic radius for metals. But for non-metals, we'll take oxygen. Oxygen wants to gain 2. So in other words, if you gain weight, you're bigger. So for a non-metal, which is bigger, the atomic radius or the ionic radius? Well, for non-metals, if you gain, the ionic radius is bigger than the atomic radius. Those two are very important points. All right? Okay, we're good.